Okay, so the day 3. Proof by induction. So there are three axioms we will be using it. So the first one is let P and B predicate. Number 2, PK be true. If PK true, then PK plus 1 should be true. So in this case, when we talk about K means either 0 or 1 or 2. So K is an integer. So let's solve number 1. This example 1. 1 plus 2 plus 3 plus n is equal to n plus 1 over 2. So step 1, let's check whether it works for 1. So n is n plus 1 over 2. 1 is 2 over 2. So 1 is 1. So it works for 1. So if it works for 1, it should work for k plus 1. So this is our left hand side. This is our right hand side. Now, step 2, left hand side. So 1 plus 2 plus 3 plus k plus 1. So we already said that this guy is k plus 1 over 2, and this part is plus k plus 1. So k squared plus k plus 2k plus 2. So k squared plus 3k plus 2 over 2. So this is our left hand side. Now we have to check the right hand side now. This is our right hand side. If we get the same right hand side, then we prove it by induction. So n plus 1 over 2 k plus 1 over 2. So k plus 1 plus 1 over 2. So k plus 1 k plus 2 over 2. So k squared plus 2k plus k plus 2 over 2. That gives us k squared plus 3k plus 2 over 2. So indeed this and this are same. So left hand side is equal to right hand side. True. We're gonna do the next example. Example number 2, which is similar, is 2n plus 1 over 6. Now we have to prove by hypothesis that by induction that the left hand side is equal to right hand side. Left hand side is a long line. It's like forever. Forever is equal to n plus 1 parenthesis 2n plus 1 over 6. So step 1. Let's plug in 1. N squared is n plus 1, 2n plus 1 over 6. 1 squared is 1 plus 1, 2, 1 plus 1 over 6. So 1, 6 over 6. So 1 is equal to 1. So it works. It works for it works for 1, so it should work for k plus 1. Okay, so now 1 square plus 2 square plus 3 square plus n square. So this is our left hand side and this is our right hand side. Our goal is to make sure that left hand side is equal to right hand side. So step 2 is left hand side. So n square, instead of n square we're going to write k square plus k plus 1 square. Then step 2 is, this one should be write this one k plus 1 2 k plus 1 over 6, and this is plus k plus 1 square. So this is k square plus k 2k plus 1 over 6 plus k square plus 2k plus 1. So 6 k square, so 2k cube plus k square plus 2k square plus k plus 6k square plus 12k plus 6 2k cube plus 9k square plus 13k plus 6. This is our left hand side. So we have to now make sure that our right hand side is this one. Step 3, the right hand side. Okay, so the right hand side is this guy, n plus 1, 2n plus 1 over 6. So remember, n will replace by k. So here you see n, you can write k. So the next step is, here you see you will write k plus 1, k plus 1 plus 1, k plus 1 plus 1 over 6. So k plus 1, k plus 2, 2k plus 2 plus 1, this is 3 over 6. So k square plus 2k plus k plus 2, 2k plus 3, 3k plus k, 2k plus k is just 3k. Now we're gonna file it. So 2k cube plus 3k square, done with this one, plus 6k square plus 9k, we're done with this one, plus 4k plus 6, all divided by 6. 2k square, k cube plus 9k square plus 13k plus 6, all divided by 6. Let me check. 2k cube plus 9k square plus 13k plus 6, all divided by 6. So right hand side. So we claim that left hand side is equal to right hand side is because left hand side is 2k cube plus 9k square plus 13k plus 6 is divided by 6 is equal to 2k cube plus 9k square plus 13k plus 6, all divided by 6. Now we're going to do more example. Example number 3. an equation for sum of a first odd integer or positive integer, then prove by induction. One. So 1 is 1. Okay. 1 is 1. This is 1 square. What is the next odd integer? 3. So 3 equal to 3 plus 1, which is 2 square. So 5 is equal to 5 plus 4, which is 3 square. What is the next positive odd integer? The next positive odd integer is 7. So 7 is 7 plus 9, which is 16 whole square. So we see the pattern. So that must be n square. So this is n squared, this is n squared, this is n squared, this is n squared, and the next one has to be n squared. Let's check. The next odd number is 9. So 9 is 9 plus 16, which is 25. 25 is 5 squared. Okay, now how can we use that to write the equation? So equation must be 1 plus 3 plus 5 2n minus 1 equal to n squared. So we wrote the equation. Now we have to prove it by induction. Step 1 is super easy as always. So step 1 is plug in number 1. 2n minus 1 is equal to n squared. So 2, 1 minus 1 is 1 squared. So 2 minus 1 is 1. So 1 is 1. So it works for 1. So it should work for, if it works for 1, it should work for k plus 1. So step 2. Step 2, left hand side. So the left hand side is this guy, 1 plus 3, 1 plus 3 plus 5 plus plus 2n minus 1. Okay, so we may see n, we're gonna write k. So 1 plus 3 plus 5 plus 2k minus 1 plus 2k plus 1 minus 1. So this part is supposed has to be n squared. So this is k squared, and that plus 2k plus 2 minus 1. So k squared plus 2k plus 1. So this is our left hand side. Now we have to find the right hand side. If the left hand side is equal to right hand side, then we prove it by induction. The right hand side is easy, is n squared, because here n squared. So whenever we see n, we're gonna replace it by k squared, and then we're gonna write the k plus 1 thing. So k plus 1 is squared. So k squared plus 2k plus 1. So this is our right hand side. So left hand side is equal to right hand side. As we see, k squared plus 2k plus 1 and k squared plus 2k plus 1. So proof by induction. The another problem. So we're gonna do lots of induction problems. So to make sure that you get the hang of it. Okay, so the next one is use induction to prove 1 plus 2 plus 2 squared plus plus 2n plus 1 minus 1. So as always, let's check for 1. Step 1, check for check for 1. So let's say 2n is equal to 2n plus 1 minus 1. So 2 1 is 2 1 plus 1 minus 1. Okay, so this is do check for 0. Step 1, check for 0. So 2n is 2n plus 1 minus 1. So 2 0 is 2 0 plus 1 minus 1. So 1 is equal to 2 minus 1. So 1 is equal to 1. So as always, if it's work for 1, it should work for k plus 1. So step 2, left hand side. The left hand side is 1 plus 2 plus 2 squared plus 2k. So 1 plus 2 plus 2 squared plus 2k plus 2k plus 1. So this one gonna be replaced by this one, gonna be replaced by the right hand side, and the right hand side is 2k plus 1 minus 1 is plus 2k plus 1. Okay, now what are we gonna do? This and this 2 times 2k plus 1 minus 1. So you're gonna put 1 over here. So now 2k plus 1 plus 1 minus 1. So 2k plus 2 minus 1. This is our left hand side. Now we're going to solve it for right hand side and make sure that the right hand side is exactly this one. So left hand side is going to be equal to right hand side. So right hand side, this is step 3, and that is 2n plus 1 minus 1. Whenever you see n, we replace it by k. So now 2k plus 1 plus 1 minus 1. So 2k plus 2 minus 1. So this is our left hand side. This is our right hand side. So now the left hand side is 2k plus 2 minus 1, and the right hand side is 2k plus 2 minus 1. So right hand side is equal to left hand side. So you prove it by induction. Now you're gonna do one more, probably 2 more. Now this time you're gonna do the geometric progression. By now it should be very easy for you to understand it, because we've been doing it since yesterday. Proof by induction is very important. It's a very important for computer science. So that's why discrete math, we don't call it just discrete math, we call it discrete math for computer science. Okay, all right. So sum of geometric progression. So sum of geometric progression. Okay, now that's sigma j goes to 0 to n a r j is a plus ar square plus ar raised to n is equal to ar n plus 1 minus a over r minus 1. All right, let's see how it goes. It's just same step. We're gonna see whether it works for 0. If it works for 0, it should work for anything else, for k plus 1. So check for 0. So a and 0 is equal to a r0 plus 1 minus a over r minus 1. So a1 is equal to a r0 plus 1 minus a. So a r minus a is r minus 1. So this is a, this is a r minus 1, r minus 1, minus 1, r minus 1, cancel, a is equal to a. So it works. If it works for any k, it should work for k plus 1. Now that's what we're going to check, whether it works for k plus 1. So step 2 is left hand side. And left hand side is a plus ar plus ar square plus arn. So every time we see n, replace it by k. Now we're going to write a plus ar plus ar square plus ar k plus ar k plus 1. Now this guy plus sign is missing. Now this guy is over here, a r k plus 1 minus a over r minus 1 plus a r k plus 1. So now we need to use algebra. So a r k plus 1 minus a plus r minus 1 a r k plus 1. Okay, so a r k plus 1 minus a plus, here is kind of tricky. You put 1 over here and you solve it. A r k plus 1 this one comes from here, then minus a r k plus 1 all divided by r minus 1. So the good thing is this guy cancel. So you write a r k plus 1 k plus 2 minus a over r minus 1. Okay, so this is our, let's say this is our left hand side. This is our left hand side. Now we're gonna solve it for right hand side, and if the right hand side is exactly like that, then we're gonna accept it. So the right hand side is right hand side is a r n plus 1 minus a all over r minus 1. So as we've been doing it for a long time, every time you see n, you replace it by k. They look good now. So you're gonna write a r k plus 1 minus a r minus 1. So a r k plus 2 minus a over r minus 1. So now you see that this is the right hand side, and this is the right hand side, and this is the left hand side. So right hand side and left hand side. So the right hand side and left hand side, they are equal to each other. So that means that we prove it by induction. So when you see right hand side and left hand side, they are equal to each other, then we're gonna write we prove by induction by